Hello, everyone, and welcome to this part of the class. We are going to be talking about the strength of materials. Now, before beginning, I want you to know that this is like the name of the topic. But first, something that is important to point out is that the name, this part here, strength. Now, look, I want you to have this clear idea in this case. There is a common mistake in the pronunciation of the word. In this case, the pronunciation is strength, okay? Strength, not strength, okay? This is a common mistake, so this is not good, okay? Now, in this case, strength works like resistance, okay? Normally, strength is associated with force, and this is still true here, but its main function is like the resistance of the materials. Why? In Spanish, the name of this topic is resistencia de materiales. So the official name in English is strength of materials. That's why I'm telling you that in this case, strength is more focused on resistance than on force. It is also in the concept of force is also included, but it is focused mainly on resistance. Okay, so this is the strength of materials. Let's begin. So we have the strength of materials can be simply defined as the ability of a material to resist the application of force. Look, the ability of a material to resist the application of force. This is what I was telling you. The focus is mainly on that, right? Resistance. Now, the effects of dynamic loading are probably the most important practical part of the strength of materials, especially the problem of fatigue. Now, I want to stop here for a little while and tell you about this part. When we talk about dynamic loading, we are referring to, let's clarify this part because this is really important. Load. Now, load, we are not talking about something like the internet, right? Loading, we are talking about an applied force. Okay, so dynamic loading means that a force is going to be applied on a specific element, and it is going to be this dynamic means that it will be moving. It will be shock after shock. That means that it is a force that is going to be, in this case, affecting a structural member. For example, I don't know, a piece of wood. And imagine that you have your hand and you're going to be hitting the piece of wood several times. This is dynamic loading. Dynamic because your in this case your knuckles or your fist, your hand is going to be moving a lot when it is applying the force to the piece of wood. So this is dynamic loading. Okay, remember, load in this context is an applied force, and dynamic loading is when we apply several times a force to a member, for example, a piece of wood. Imagine that you're hitting the wood a lot of times. This is dynamic loading, and how much that piece of wood can resist this dynamic loading. This is like the logic, okay? So the effects of dynamic loading are probably the most important practical part of the strength of materials, especially the problem of fatigue. Now, to clarify this fatigue, we can go back to the idea of the piece of wood. If you start hitting the piece of wood a lot of times, let's suppose that you use a hammer to hit the wood, eventually the wood is going to start cracking, right? You're going to find some cracks. You're going to find this tendency to break. When the wood starts to have a clear tendency in breaking, we can talk about fatigue. This is like the idea of that. When the material cannot longer resist the application of force. Loading has been so much, or dynamic loading has been so much, and it cannot hold everything. So that would be those would be the main concepts of the strength of materials in general. It says the study of the strength of materials is concerned specifically with the following issues. So we have three different perspectives. It says the internal forces of a member caused by the external forces acting on the member. Now, how is this possible? For example, imagine that you have in the palm of your hand, you are holding something really heavy. For example, a big box. Let's suppose that the member is your hand, or your arm and your hand. This is the element that we are structurally analyzing. We are analyzing the arm and the hand. This is the element that we are analyzing. So the external force, let's suppose that you are holding the box up, and the external member is precisely the box, right? Because it's the member that is affecting the element that you're analyzing. Which element are you analyzing? The hand and the arm, right? So the internal forces are the microscopically detectable forces inside the palm of your hand holding that box, right? This is like the logic. Inside your hand, there are little forces on all the surface of your palm that are actually holding the box, right? And the external force is precisely the box, right? Number two, the changes in dimension of a member caused by their forces, by these forces. Now, changes in dimension means if there is an extension of, for example, the length of something. Let's suppose that we have a rubber band. If you stretch the rubber band, the dimension of the length of the rubber band is going to increase. This is a change in the dimension. This is another issue that is important in strength of materials, okay? So that's how the logic is going to work, okay? Number three, the physical properties of the material the member is made of. Now, there are certain characteristics that we are going to identify that happen in a specific material. Regardless of the size of a material, some materials can have specific behaviors according to certain forces. For example, we cannot expect a piece of wood to react in the same way as a piece of steel when we are applying shock. That means when we are hitting, for example, with a hammer. If we are hitting with a hammer a piece of wood in comparison to a piece of iron, evidently the iron is going to resist more. These are the physical properties that we are talking about here, okay? Again, the changes in dimension, extension, or maybe reduction of the sizes of the width, the length, or the depth of a material. Then we have the physical properties. We are going to identify some variables that have been standardized. These variables, we are going to specify them during the class of the different materials. For example, again, the resistance of the iron is a lot different than the resistance of the wood, and they are going to react differently. For example, let's talk about glass. Glass is very stiff. The glass is a material that it's very rigid, but rigidity doesn't mean that it's not going to break. In fact, as you know, glass is more easily breakable. So those are the physical properties that we're going to reveal. Again, the glass can be strictly rigid and solid, but it's easily breakable, right? And we are going to be focused precisely on the static. This is something that has been learned in the part of mechanics, right? Statics is the study of a behavior of rigid bodies at rest, right? This is something that has been spoken in another video, in another class that is directed to mechanics, but we are just clarifying that our focus is on mechanics. Now, look at this. Let's talk about this little introduction. Although most of these bodies, the bodies that we're going to examine, a piece of wood, a piece of concrete, a piece of metal, whatever, are not absolutely rigid, we have this property, the assumption of rigidity. So we have to clarify this. There are no materials around the world that are perfectly rigid. This is a lie. This is something that is not true. Okay, all the materials, even though they look perfectly resistant, for example, a piece of titanium, for example, internally they have little deformations. So in reality, there are not perfect materials that can be completely rigid, right? There will always be an internal reaction that it's going to make them deformable. But for practical terms, and since we are studying the basis of engineering, in this case structural engineering, we are not going to be paying attention to those little deformations. We need to assume, that means to consider the materials as rigid. Remember that we spoke about rigidity in another video where we spoke about rigid bodies. This video is also about mechanics. That's why it was the basis of the current class. So this is like the logic, okay? We are talking about the assumption of rigidity. Even though we are talking about a piece of wood and we can say this is easily deformable, we are going to assume that wood it's not easily deformable, okay? So it says, the assumption of rigidity is valid for the purpose of determining the reactions of the system. Now, what is this situation of the reactions of the system? Now, reactions, we're not talking about being happy or being sad, right? This is human reactions. Reactions means those forces that appear as a result of the action of previous ones. For example, if you hit the wall with your hand, it is going to be hurtful for you because the wall is reacting with an equal force but opposite, like talking about the third Newton law of motion that we already spoke about in the part of physics. So this is like the logic here, okay? We are talking about reactions are forces that work as a response to initial forces. For example, if you try to, let's suppose that there is a loaf, I'm going to write that word. So let's suppose that you have a loaf. A loaf is a piece of bread, right? And you try to break it internally, it will try to not getting broken, right? Not being broken, I mean. So let's imagine, for example, a ledge, right? A ledge is like a platform that comes out of a mountain or an extra space in the building. You have seen those movies where people come out of a window and they can step on a border. This is a ledge, right? When people step on a border, in this case a ledge, when they come out of, that's a tall building or a tall house, and there is this extra portion of platform outside the window, and someone is trying to get outside the window and step on that extra space. When they stand on the ledge, internally the ledge is reacting to that weight, right? Because if the ledge is not sufficiently strong, it can break depending on the material. If we are talking about a concrete ledge, obviously is going to resist a a human body. But if, let's suppose that a ledge is made of wood, it might break precisely of that. It will try to hold the person, but it can eventually break. This is the reaction of the system. We step, there is a downward force of our weight, and the reaction is trying to stop that force and trying to hold upwards, because if we step on the ledge, the force goes down, and obviously the reaction is going to go up. Now, this is not a general rule. We are not talking about that for every force that goes down, there is a unique force that goes up. No, there can be several reactions, in this case, forces that can, like in a group, in a big cluster, work together to make the opposite effect of the downward force. This is like the logic. So it says, actually, every material will get deformed under a load, what I was telling you. Even concrete, this is very important, even concrete will microscopically deform, right? When a person walks on it. So we are just assuming. External loads on a structural system create resisting forces within all the members of that form the load path from the load's point of application to the ground beneath the foundation. This is what we were talking about with the ledge, okay? This is like the logic. There will always be, for example, if you step on a ledge outside a window, you are the external load, and you are going to create resisting forces. These are like the little reactions within the structural member, okay? That's the logic. Let's continue. Now, these definitions are very important, okay? And we have to learn the way in which we are going to calculate them. Now, we are going to learn the basics in this part, and then we're going to extend the application in another way. So it says, the following are basic definitions and equations used to calculate the strength of materials. Stress. Now, when we are talking about the stress, we are not referring to our bad day, a lot of work, a lot of homework, being like completely like psychologically affected because you have a lot to do. That's not the type of stress that we are referring to here. When we are talking about stress here, it is related to force, specifically a load. Let's check the definition. Look, it's the ratio of applied load to the cross-sectional area. Let's mark this. Applied load to the cross-sectional area of an element. This is like the essence of the definition, okay? This is like the essence of the definition. Applied load can be the weight of a body, or the weight of a box, or the weight of a bag, to the cross-sectional area of an element. Now, this is another important concept. Cross-sectional area. What is a cross-sectional area? Now, this is something that we have to keep in mind. For example, let's suppose that we have a big cylinder. Not talking about a concrete cylinder. Let's suppose a sausage, right? This type of food. The sausage is mainly a cylinder. It's not completely a cylinder, right? But it's mainly a cylinder. And let's suppose that you're going to cut the sausage, and you're going to cut the sausage using a slice across the width of the sausage, not the length, because if you cut the sausage through its length, you're going to get two long pieces. No, I'm talking about two pieces that will, when you cut it in half, but like cutting it across the width, not the length of the sausage, you're going to acquire a circle has two faces, right? When you cut the sausage, let's suppose that you cut the sausage like in the middle, you are going to get, and you move those partial parts to the front, you see two circles. This is the cross-sectional area of a sausage. That means that if you cut it, you're going to get a circle as the cross-sectional area. Another example is, let's suppose you have a cylinder. If you see a cylinder like a bar, if you take the bar and move it and look to one of its ends, you're focusing your sight on one of the ends of the bar, you're not going to see a big line. You're going to see a circle. This is the cross-sectional area of a cylinder. The same happens, for example, if we're talking about a long piece of bar that has squares at the end. These squares are the cross-sectional area. If you could cut that piece, that bar, that rectangular bar, if you cut the rectangular bar, you're going to get a rectangle. This is the cross-sectional area, not a long line. Okay, so that's what happens. To make it even in a simple way, let's suppose that you have a ball, right? A ball of mass. Let's suppose a soccer ball, but instead of having this rubber material, let's suppose that it's a sphere. To be more specific, you have a sphere. If you cut the sphere exactly in half, you're going to get a circle as a cross-sectional area. Okay? It's like changing from 3 dimensions to 2 dimensions. When you can change something into 2 dimensions, you are going to get the face of those objects. This is a cross-sectional area. Okay? So again, as a summary, we have a sphere and we cut the sphere by the half. When you cut the sphere by the half, you're going to get a face of a circle. Okay? Let's suppose that you have a melon. When you cut the melon in half, the front that gets before you eat the melon is a circle. This is the cross-sectional area. The same happens with a long rectangular bar or a cylinder or another structural member, right? So, so we are going to make the relationship of load. Remember that load is a force, applied force. We are going to calculate the ratio. That means this division, right? You have the equation here. Stress equals load divided by area. Force divided by the cross-sectional area. So, applied load to the cross-sectional area of an element in tension or compression. This is something really important as well. Now, this is not the most technical way of saying it, but we can say that tension is a pushing force, and compression is a pulling force. For example, let's suppose that you have let's suppose that you have a Play-Doh. I don't know if, let's suppose that you have, yes, let's suppose that you have a rubber band. If you stretch the rubber band, you're applying tension. Now, let's suppose that you try to shrink the rubber band. This would be compression, okay? Those are some examples. Any material that you can stretch and then you can push it back to its original dimension, you are applying tension when you stretch it, and you're applying compression when you're trying to return it to its original length. In this case, a material that we can mention here again is Play-Doh. Now, to make it quick, Play-Doh is what we call in Spanish plasticina. When you stretch Play-Doh, you're applying tension, and when you're trying to shrink it, that means make it back to its original shape, you are compressing the Play-Doh. Let's go back. So, and it is expressed in pounds per square inch. This is a unit of measurement, or Newton per square meter, okay? Then we have a strain. Now, a strain, we are not talking about an injury that you can get when you fall or something, right? We're talking about a concept of physics. In this case, specifically, strength of materials. A measure of the deformation. It measures the deformation of the material. And it's dimensionless. That means that we don't have, for example, in stress, we have Newton per square meter. In strain, we don't have a measurement because we are defining length divided by length. Here we have the calculation. Look, strain is changing length divided by the original length. We have delta L divided by L, or initial L. So that's like the logic here, okay? So again, there is no dimension. We don't have Newton, we don't have joules, we don't have meters, nothing like that. We are just measuring like a relationship between deformation. And then we have the modulus of elasticity. Now, modulus is simply an indicator, okay? A modulus is an indicator. Since the stress is proportional to load and the strain is proportional to deformation, this implies that the stress is proportional to strain. So look, going back, for stress, we are going to use this letter, which is sigma. Sigma is a Greek letter, okay? A Greek letter. And strain, we are going to use epsilon. Epsilon is another Greek letter. So the modulus of elasticity, some people call Young's modulus is a synonym of the modulus of elasticity, okay? A synonym is Young's modulus. So some people call it Young's modulus. Since the stress is proportional to load and the strain is proportional to deformation, this implies that the stress is proportional to strain. A division of the two, sigma divided by epsilon, stress divided by strain. So we have the calculations here. You can see the equations. Let's continue. Definitions. It says Hooke's law is the statement of that proportionality. That means that the proportionality of modulus elasticity comes from Hooke's law. There we go. Look, the constant is the modulus of elasticity, Young's or the tensile modulus. So we have three synonyms. And is the material's stiffness. Stiffness is the how rigid, right? Like the rigidity, right? If a material obeys Hooke's law, it is elastic. That means that we can proportionally stretch it, for example. Now, we are going to start with a series of definitions that I am going to make use of a picture to make it easier for us to understand the these definitions, okay? So let's go to the, we are going to read some of them, and then we are going to use a graph to have a better understanding. Okay, so let's read some definitions. Proportional limit. The greatest stress at which a material is capable of sustaining the applied load without deviating from the proportionality of stress to strain. This would be like the essence, greatest stress that the material can hold without losing the proportionality. That means that after a specific stress, that proportionality is lost. We are going to check this later in a graph. As I told you, I am going to use a graph to show you these definitions. Let's continue. Ultimate strength. Now, I want to clarify something. Ultimate is not the last one, okay? Normally, there is a confusion with this concept because people think that ultimate is the last one, and this is not correct. Ultimate is the maximum, okay? Not the last one. The maximum, the highest level, but not the last one. Why? Because in Spanish we say último, and people think that ultimate is related to último, and sometimes it is translated as esfuerzo último. This is not correct, okay? It is the maximum, okay? Not the last one. The maximum. Let's go back. So ultimate strength, maximum stress, a material stands when subjected to an applied load. I would say that this is the essence of the concept. Dividing the load at failure by the original cross-section area determines the value. As simple as this, the maximum stress, remember that stress is force divided by area or load divided by area, a material stands when subjected to a load. And we have the elastic limit. this is a point on the stress strain curve, we will, like I told you a little while ago, I am going to use a graph to show these concepts. This graph is precisely the stress strain curve, okay? So it says the point on this graph beyond which the material permanently stays deformed. After this point, the elastic limit, there is no return. The material will stay deformed forever, right? That means that it will not recover its original shape, okay? So when we break the elastic limit, the material cannot return to its original shape. Imagine a rubber band. If you overstretch a rubber band, it will eventually get overstressed and it will not return to its exactly original length, okay? Then we have the yield strength. Now, this is a very interesting word. Yield is to give control to something else. That means you are trying to resist something, but you cannot resist anymore, and you decide to surrender, right? You decide to stop. You cease the resistance, and there's no longer resistance. That is what happens. Yield strength, it says, point at which material exceeds the elastic limit and will not return to its original shape or length if the stress is removed. That means we have applied so much force that the material is going to say, I cannot hold this force anymore, and I will not resist. And that means that the material will be permanently deformed, okay? These two are very associated. The difference is that here we are saying that the material has a specific limit of resistance, of holding and trying to return to its original shape, and when you break it, it will never return, right? It will like surrender to the pressure, okay? In this case, to the load. So we will proceed to the next definitions. Now, in this case, we have Poisson's ratio. This is Poisson, okay? Please, we have to keep in mind something. Ratio is a relationship between two numbers, right? We can say that is like a proportion. So it's like dividing a number into another number and getting an indicator. This is the ratio, right? It's like an indicator, a relationship between two numbers. And when we divide them, we get an indicator. This is like the logic. So in this case, the Poisson's ratio is the ratio of the lateral to longitudinal strain. Now, this means that we are focusing on two different dimensions of an object, two different dimensions of an element that we might be analyzing. Since we are making a relationship between two sides, we have something dimensionless again, right? We don't have dimensions because we are making relationship of two little distances, right? We will check this in a little graph just to make it a little bit easier to understand. So it says it's a dimensionless constant used for stress and deflection analysis of structures such as beams, plates, and rotating discs. We will talk about this element later on, okay, the beams. So here we have the relationship, right? So it says, we already talked about the strain, right? Remember that we talked about the strain here, and it is like a degree of deformation. It is like an indicator of deformation. So here we are making the relationship of the deformation of the lateral dimension to the longitudinal dimension. So we are going to use a graph to understand a little bit better the focus. Here, we can see the Poisson's ratio. Now, look, let's suppose that this is like a little bar. This long side is the longitudinal side, and the width, or this, you see the two arrows facing to each other. Imagine this little rectangle. The long side is the longitudinal side, and the short side, the vertical one, is the lateral side. So this Poisson's ratio is going to give us a relationship between these two elements in a piece of material, right? Um, so let's go back to the relationship here. So as you can see, if we have a longitudinal strain greater than a lateral strain, we have a small Poisson's ratio. So Poisson is going to give us an idea of how the deformation works in a specific material. If the deformation is stronger in the lateral side, or it might be stronger in the longitudinal side. This is like the logic of this concept, okay? Okay, now we can continue with bending and stress. Now, first, it is important to know that when we say bending, we are talking about a characteristic in which we are going to change something that is originally straight or almost straight, and we are going to give it a curved shape, right? It can be like when you have a rod, for example, a rod made of aluminum, and you start curving it, and it will acquire a new shape, right? This is bending. Again, it's changing something that was straight into something curved. So, and stress, as you know, we already know this concept from this class, is related to force and area, right? So let's speak about the bending and stress. So when bending a piece of metal, one surface of the material stretches in tension, while the opposite surface compresses. So we have tension and compression, right? There is a line of origin of zero stress between the two sides of the beam. Again, just to make a little idea here, I'm going to highlight this with a distinctive color. For example, this cyan one. A beam is a structural member. It can be a piece of metal, it can be a piece of wood, it can be a bar made of any type of material, right? So we have a region of tension, a region of compression, and a region of zero stress. But between the two sides, we have a region of zero stress. This is called the neutral axis. So we have the tension, the compression, and the neutral axis. These are like the three perspectives of the beam, where the beam doesn't get compressed, neither tensed. So let's check a little picture to understand this. Look, this is a good example. This is a beam. Again, it can be a bar, and these are two supports holding the bar. And we get a force, and we apply a force that changes the original straight horizontal shape of the bar and curves it. As you can see, this can be straight, and it curves it like this. So we have a downward force that curves it. On this side of the beam, we have compression because there are like microscopical pushing forces on that side of the beam. And on the other side, we have tension because the surface and part of the internal structure stretches, right? You can see this experiment with your fingers, right? If you pull your finger to the back, let's suppose that you have your hand and you have the palm of your hand is extended. You can pull your fingers, and you are going in the joints. You are going to find tension. But if you on the like changing the style, instead of pulling your fingers, like you have your palm and you pull your fingers, now you can make your fist. When you make your fist, you see that the joints are, in this case, a little bit loose because there is a little compression, right? There is a little compression inside instead of a tension. The same happens here. And in the middle, there is a little part in which there is a neutral action of the force. There is neither force nor, there is neither compression nor tension. and this is the neutral axis that we were speaking about, right? So this is a graphical example. Again, on this side we have pushing forces, this is compression, and here we are stretching the surface, so we have tension. Let's continue. We will continue with the definitions. Okay, so moving on, the supplementary definitions, we have yielding. It occurs when the design stress exceeds the material yield strength. Remember that we spoke about yield strength. This is a specific point in which the material can no longer hold its elastic property and becomes plastic. Yielding is like the property, right? Yield strength is the specific point in which it happens, but the property in general is yielding, right? The yield point of a material is defined in engineering as the stress at which a material begins to plastically deform. So this is the yield strength that we spoke, right? The stress at which a material begins to plastically deform. Now, this is the yield strength, right? Or the specific point. But yielding is the property, right? This is the characteristic of a material in which it starts surrender. It starts to surrender, right? And it becomes plastic. It can be elastic, and now it becomes plastic. Then we have the fatigue. Is the progressive and localized structural damage that occurs when a material is subjected to cyclic loading. Remember, load is the application of force, and cyclic means several times applying consistent force on a structural member. So fatigue is the progressive and localized structural damage. When a piece of concrete starts cracking or starts showing a little deformation because of the shock applied, it's reaching its fatigue, right? This is like the logic. So these are the two supplementary concepts, right? Now we are going to check the graph. It is handmade, but it clearly shows the logic, right? Before going there, as you can see, the last part here we have the stress strain curve. This is the graphic that we are going to study right now. Look, the relationship between the stress and the strain that a material shows is known as a stress strain curve. So this is the graphic relationship between the stress and the strain of any type of a material. It can be any type of material, okay? It is unique for each material. This is important. It is unique for each material. This is very important. There is no standard in the stress strain curve. Every single material will show a different pattern. And is given by plotting the amount of deformation at distinct intervals of tensile or compressive loading. For example, here we have strain and stress. We have concrete, this is a shape, cast iron is another shape, and mild steel is another shape. Let's check the stress strain curve from a general perspective. So again, this is handmade, but it's pretty clear. So let's start with a little explanation here. So in this case, we have, this is the axis of the strain, and this is the axis of the stress. Remember, strain is dimensionless, and stress is Newton per square meter. There are other types of measurements, but this is like the international system standard. So we have, let's suppose that we are stretching a material. Imagine that you are stretching a spring, okay? Let's suppose that we are going to be stretching a spring. This is like the logic that we are going to use right now. Okay, with this new image that I am showing you, the idea is to have this perspective. We have a spring, and then we are going to hang, in this case, a little weight on the spring, and we are going to be adding, imagine that there is a magnet here, and we are going to be adding a little bit more, a little bit more, a little bit more, and as we move from left to right, we are going to increase the stress and the strain, the two elements are going to change. So imagine that this is the situation. Let's go back to the graph. So moving from left to right is what is happening hypothetically to this spring, right? We are stretching the spring, and this is like the behavior. So as we move from left to right, it's like moving from left to right on this graph. So look, we have an initial part that has this straight line. That means that there is a proportionality. If there is a proportionality, we can use an equation to model the proportionality. And the equation, as we already talked about, is the modulus that we spoke about, in this case, the Young's modulus, or the modulus of elasticity. That's why it is, in this case, proportional. So we can say that Young's modulus equals stress divided by strain. As you can see in this part, this is a linear equation. Remember, in math, when we were speaking about, when we speak about a linear equation, we use the equation y equals mx plus b. In this case, it is something similar. The dependent variable would be stress and the independent would be strain. So we have stress equals the modulus of elasticity times the strain. So there is a point. So as we move, the spring behaves in a proportional situation, because remember, you can stretch a spring and it will recover its original shape. This is because the spring is elastic. That means that the spring can recover its original shape. There is a property of the spring is elasticity, but there is a limit for this. If we stretch it so much, it will break. I'm not talking about the spring. It will stop being elastic and it will start being plastic. That means that it will never return to its original shape. So that's what we have here. As we start stretching the spring, we move from left to right, and there will be a moment in which the proportion is broken. They are still somehow proportional, but we cannot model it with a linear equation or function. And there will be a moment in which the spring will stop. It will lose its elastic property and it will become plastic. This is the yield strength. The exact point on the graph in which the spring will no longer return to its original length. So as we move to the right, this is an irregular behavior, and there will be a moment in which the spring will reach its ultimate strength. That means the maximum stress that the spring will withstand is a synonym of resist, right? The maximum strength that the spring will withstand without breaking, without like cracking, we can say that, right? It can hold. This is the top level of this is the top level of the strength that the spring will be able to hold until it starts cracking or internally breaking. After this point, the spring will start internally cracking until the rupture happens. That means the spring breaks, because they are not eternal. They are not completely unbreakable. So there will be a moment in which the spring will break, and this is the rupture strength. For example, here in the little graph, we can say that this point is really close to the rupture part, right? Because obviously in this part it is plastic, and it's getting close to its rupture. So there we go. Let's go back. So this is a curve that can help you to get the relationship there of the variables, and it is visually a little bit easier to understand the topic. Remember, if you don't understand the definitions, you can always go back to this graph, and this graph will be your reference. So let's continue. Now we have beams. I'm going to go back here. Look, this is the definition. A beam is a structural member A beam is a structural member which carries loads. This is a simple but very effective definition. Just like you can read here, this is the definition. We don't need something more elaborated than that. So it is a structural member that will hold, it will carry loads. In other words, the application of force. These loads are applied generally perpendicular to its longitudinal axis. That means that the force is going to be applied on the longest side. We will check examples to understand this, or pictures in order to understand this in a better way. There we go, the longitudinal side, in other words, the longest side. Normally the application of the load is perpendicular to the longest side. Often they have a rectangular cross-sectional shape. We already talked about cross-sectional area, but they can be of any geometry. It can be circular too, right? Or even a triangle. Beam types are determined by method of supports. Now, we will talk about supports right now, not by method of loading. That means that the way in which we classify the beams, it's not according to the type of load it is receiving. We classify the beams according to the supports that the beams have. The beam types are simple and cantilever. We will check that right now, and we will check the differences. They are statically determinable. Now, what is this? What is statically determinable? We can use Newton equations or Newton laws of motion in order to determine certain forces. Let's check the example here. Look, this is a visual example of a beam. This horizontal bar is the beam. As you see, the force is applied in a perpendicular way. This is the longitudinal side of the beam, and the force is applied in a perpendicular way to this longitude. Not always, right? Not all the times the force is going to be applied in a perpendicular way. But if it is not applied in a perpendicular way, and we have a diagonal way, it will always have components, right? So this little triangle here and this little circle are the supports. Remember that we were talking about supports. So the supports are precisely the things that hold the beam. In this case, the triangle is stuck on the foundation or stuck on the floor. That means that the reaction is horizontal and vertical. The beam will not move vertically or horizontally. Now, in the case of the circle, since the circle can roll, this can move in a horizontal line, the reaction is only vertical, because vertically you cannot take this down because it's being held by the circle. But horizontally it can roll, right? So you can displace the beam in this side. So these are two types of supports, right? And the supports create reactions. For example, here, as I told you, this one will create a vertical and a horizontal reaction. And the circle will create only a vertical reaction, okay? L is the length of the beam, right? So remember, that's like the logic. We can use, for example, we can use some shapes in order to see this. For example, the arrow. Now look, there will be a hypothetical reaction here, a vertical one. I'm going to use this black version, and a horizontal one, right? Remember, in this case, we are going to have vertical and horizontal here on this support, which is a triangle, whereas on this side, we are only going to have a vertical version, okay? Here we go, because it can roll. There we go. Okay, so let's continue. We were talking about the two types of beams. simple and cantilever. Let's check them. Now, this is a simple one, okay? The original one. This is a simple one. It is it is on two reactions. This is a simple one. And then this one, imagine that this is the wall. This is the beam. It is a stock. It is like not inside, right? But it's we can use specific type, maybe nails or screws or something to make it fixed. That means fixed means that it cannot be moved. It is fixed on the wall. So it's like hanging, right? And we have a free end. So imagine your arm and you place your arm in a horizontal way. This is like a cantilever beam. That means that this one, the simple one, is on the floor and this one is on the wall. And only one side is being held by, for example, the screws, for example. So this is a cantilever. Now, for these two types, there is a common situation, and it's because they are statically determinable. That means that we can calculate the reactions. Precisely, reactions are these internal forces of the supports. For example, we have a vertical and a horizontal one here and a vertical one here. We can calculate this using Newton's laws of motion, or maybe using an analysis of torques. We can calculate these reactions. The same here, because the fact of having a fixed end, it's because we have a possible reaction holding here. So, and we can have another weight here. We can place a box here, and we can calculate the reactions as well. Let's move on. So look, simple and cantilever, they are statically determinable, meaning that the reactions in the supports, shears, and moments can be calculated using, there is a missing part here, but we can be calculated using the analysis of Newton's laws of motion or using the torques, as I told you before. Let's continue. Now, we have continuous beams. This is different. They're statically indeterminate. That means that we cannot calculate the reactions of these types of beams utilizing Newton's laws. We need something else. So let's read again this part. Continuous beams are statically indeterminate. The internal forces of these beams cannot be found by using the laws of static alone. These laws of static are the ones that we spoke on physics about Newton's laws, okay? So that's the logic. A number of formulas have been derived to simplify their analysis. So, before continuing, let's check an example of continuous beams, right? Look, this is what we call a truss, okay? In Spanish is armadura, but we're not talking about the body armor, for example. No, we're talking about, this can be like a bridge, right? When you go to some places of the world, you can see that in order to join and for cars to be able to make it from one side to the other in a gorge, for example, or maybe not a gorge, it can also be a cliff. There is a bridge, and this might be the shape or the style of the bridge. We have an upper chord, a lower chord. The span is this length, right? And the rise, how tall it is, and these diagonals. Now look, why cannot we use the Newton laws? Because it has a lot of elements. These diagonals are internal elements. So using three equations of Newton, they are not enough. We need to use different techniques that have been developed for engineering in order to calculate the internal forces of the truss, okay? So have to keep that in mind. Let's go back. So then we have two beam loading conditions that either occur independently or combined are concentrated. That means a single force, either a force or a moment that can be applied as a concentrated load. Both are applied at a single point. This is important. Applied at a single point. That means punctually, right? Only one specific region along the beam axis. These loads are shown as a jump in the shear or moment diagrams. And we have, again, remember, these are the loading conditions, okay? Loading conditions, concentrated, or it can also be distributed. If it is distributed, imagine a pile of gravel. These loads can be uniformly or non-uniformly distributed. Let's check a picture. Look, we have concentrated and distributed. This one is concentrated. It's a single force applied in a point. But if we have a specific type of load that cannot be concentrated, for example, imagine a sack or a big box with a lot of gravel, remember, for example, a lot of gravel. If we have a lot of gravel, all piled together, it will not be a concentrated force because those little rocks in the gravel, they're like small forces that we can consider to be a general distribution of forces, like here. There are some procedures, some formulas that can convert this distributed load into a single one, okay? So we can substitute this into a single one. Remember, a lot of rocks together here, a lot of rocks can be changed, mathematically speaking, into a single force using certain formulas. But this is a distributed load and this is a concentrated load, okay? So that would be all for strength of materials. This is the complete class, and thank you for watching and learning.